is yours.
Thank you, Marco, for introduction. So it's a pleasure to be here, guys. And thank you, Marco and Francis, to organize this workshop. I personally enjoyed the morning session, the professor from Ulu and friends. So basically what I'm going to present is mainly about practical challenges. So at the end of the day, I know you guys are working on RIS, but at the end of the day, you need to fabricate RIS. And you need to consider that limitation of RIS, then go back and optimize your algorithm. So this nice building here is our Institute for Communication System. This is the largest center in the UK, working on 5G, 6G. We're working on different aspects of wireless communication, different layer, MAC layer, physical layer. And among these, I'm the lead of the Surface Electromagnetic Labs. So today, this is the content of my talk. And I would like to start with short introduction about my team. So basically in this lab, in the Surface Electromagnetic Lab, we mainly deal with the structure launched by surface wave. So currently I have 2 PhD students, 4 of them recently graduated, and Vikrant working on a perfect magnetic conductor, Anton working on millimeter wave RIS, Mariam working on line wave, Zahra working on analog computing, Shadi working on gap waveguide, Demos working on terahertz channel and RIS channel, and my senior postdoc, they mainly work on RIS and computing. And so, and now I'm also currently hiring 2 PhD and 2 postdoc. If I would like to ask you to spread the word, if you know someone good, they can join my team. So about the project, the active project currently I'm leading on only RIS, because I have some other projects on terahertz communication, but these are the main active project only on RIS development. So the first 3 is supported by government, Department for Science, Innovation, Technology, DCIT. So in Flexidas, we're working with a company from actually Korea, and they developing DAS, distributed antenna system, and we're developing RIS. But the beauty of this work, we try to control RIS and DAS from ORAN system. So in RIC, in an ORAN system, we try to manage the coverage enhancement when we get the KPI from the network. So in Core HDD, which is a very big consortium, and the project is around £7 million. So we try to deploy 5G, private 5G in one theater, and then over there, because of the limitation of the building, we try to add several static RIS. So before I start my technical discussion, please allow me to use a static RIS when I meant there is no input power, there is no diode, there is nothing, it's just fixed for particular angle. And when I say dynamic surface, it has some diode or reactor which you can steer the beam. And the third one is active RIS, or what Professor mentioned about relay RIS. We call it a static, we call it active RIS, which we deploy some transistor. So in Esconda also, we try to investigate RIS in outdoor and indoor, again, using Open RAN system. In Innovate UK, this is my recent project, we are developing LCD-based RIS with a company in Taiwan. So this is our partner. And I recently get another funding from Huawei to develop RIS for ISAC. And I also have EPSRC funding for millimeter wave RIS. So as you've seen, these are the active projects going on only on RIS. So although there is still some argue from some academia or some industry that they are doubtful about RIS, but we try to prove that RIS is going to work, and also we try to manage it from the network as well. So these are the facilities we have. So we have terahertz spectroscopy up to 2.7 terahertz. We have VNA up to 750 gigahertz. Recently, we bought one Keysight real-time oscilloscope with 33 gigahertz bandwidth, which is very good for 6G communication because you can see the bit error rate, cancellation, everything. We have a very large chamber. We have developed the world's first hybrid beamformer millimeter wave 5 years back. It still is available. If you have any hybrid beamforming algorithm, you're welcome to test it. And also we have some channel sounding equipment from Road and Shores up to 85 gigahertz. So let's go to our prototype. So this prototype I'm not going to present. Mainly you've seen it before in some of our published papers. So we try to develop a lot of RIS. This one is for 100 gigahertz, static RIS. The reflection wave is not only plane wave, it gives you OA and beam as well. So it's not only reflect the beam, it's only converting the wavefront. So this is, I believe, I've seen today morning, I've seen some nice metasurface done by other group, but this is actually the first RIS, practical RIS, because RIS is one application of metasurface, and as Professor from France mentioned that we borrow these things from optic. So long time ago, we used metasurface for metal lens, for example, for modulator. It's not a new topic, but because thanks to Marco, he brought this metasurface to wireless community, and since then there are a lot of huge interest towards RIS. So we developed this one. This one is the dynamic one, around 3,000 element with varactor diode, so you can steer the beam. The second one, which you can see, is a static. There is no input power here, all static, and it can reflect back to minus 45, positive 45 beam off to the angle, off to the axis. So the up, you can see there are two glass, but they are transparent metal surface coated on this glass. You cannot really see it. So one of them is letting the 5G signal coming to indoor environment. Another one let 5G signal come to the environment and block Wi-Fi signal to leak out. So at the same time, you improve the signal of the 5G quality in indoor, and also you improve the security of your Wi-Fi, because if you go around of this building, you can simply join and find the Wi-Fi of this building. And also we developed the STAR RIS. STAR RIS is a new topic, which you have omnidirectional type RIS. You can transmit and you can transmit, actually you can work with the reflection coefficient and transmission coefficient, but the main problem of that is very difficult to control reflection and transmission at this independently. So one of my new projects, actually, we are developing that. So we already designed and we send it for fabrication, that we try to manage reflection and transmission independently. So we did several channel measurement in indoor environment, and you can see, although it is 3.5 gigahertz, you see a lot of multipassing environment, but you see RIS try to flatten the channel. We did the same thing in outdoor environment with our active RIS, with our dynamic RIS, and we try it with both omnidirectional and directional antenna at the receiver. So these are several activities, but this is the main discussion today I'm going through. So those things I just presented is the things we've done so far, but these are the recent work, and I would be happy to share with you, and I also would be happy to discuss this during the break as well, or during this discussion. So we have several problems of RIS. The first one is a complexity, cost, and energy, which I go through it, and I will share with you what is the main reason why this is expensive, why this is complex. And then high specular reflection, which honestly, you can't beat the physics, because when the wave is coming from base station, you do your best to manipulate your wave towards any direction, still some of your energy will reflect back to your base station. Localization is very important, which we can talk about the ISAC, and shadowing. When you put a large surface on one building, behind that building, you made it blind spot. So you need to do something that you solve this shadowing. So let's start with the complexity. So this metasurface, this RIS, consists of lots of units. Why I say lots of? Because metasurface is 2D counterpart of the metamaterials. And metamaterials are those engineered material which they can things invisible. What I mean, if you have some metamaterial, and this is my blockage, you can make this invisible in point of view of electromagnetic wave. But if you want to get a metamaterial, proper metamaterial, you should design a 3D, which is bulky. So these metasurfaces are beautiful because they are 2D planar, and you can manipulate your EM wavefront in an arbitrary shape. So if you want to have do any type of polarizer, reflective, absorption type of manipulation of your electromagnetic field, you need to have a large aperture, right? And you need to have a very small size of unit cell, because when you have a small size of unit cell, you tried also at the same time to solve two problems. One, you try to reduce the specular reflection. The second, the angle sensitivity would be wide. So if you want to widen your metasurface in terms of angle, you need to make it small. But when you make the unit cell small, you are going to lose the phase range. And if you lose the phase range, you can't really steer the beam towards what you want. There are some prototypes which they are on and off. They are not RIS. They are not capable of manipulating the electromagnetic wave. They are like beam splitting. They generate two beams. So the minimum requirement, if you want to work with a digital metasurface, is 4 state, which is 2-bit. But the best one is 8 state. But the one we fabricate is analog, so you have access to all phase range. So also, when you try to make it small, you are losing the phase. So there is one solution. You can make it a stack metasurface to get this phase range, appropriate phase range. But the problem is complexity, price, and then when you want to add some diode or reactor diode, you get a stack. So in this one of our design, we try to make it small. We try to get a proper phase, and we try to, another problem of the unit cell is, when you design a metasurface, you need to consider two things. One should be polarization insensitive, because when the wave coming from the base station is coming slant polarized, two vertical and horizontal, but shifted 45 degrees, right? But when the wave is coming to your phone, is not 45, is not vertical, or is some linear polarization with some tilt angle which you don't know, right? So RIS also should be same. So RIS can sense the polarization. So your unit cell should be polarization insensitive, right? And if you want to control any polarization, so if we talk about, let's say you have analog metasurface, right? You have access to range of phase. So minimum, you need 2 diode, right? But you are going to make it small, and you need to looking for 3-bit. So for each polarization, you need 3 diodes. So together 6 diodes per unit cell. And if you have 10,000 elements, you need 60,000 diodes. This is one problem. Second problem, you want to drive this individually, because if you can't drive them individually, you get again stuck, because because you know in literature you will see RIS can do magic, right? If you want really your RIS do magic, you should control each individual element. So the best DAC or the best FPGA available is from Texas Instruments with 96 channel. Let's assume we have a DAC with 100 channel. So if you have 10,000 elements, and if you have just 4 elements, how many DAC we need? 100 DAC. And each DAC consume around 2 watts, roughly. So you need 200 watts. Who is going to pay for it? So these are the basic problem, and these are the things we need to solve it. So in this practical work, we try to minimize the size, lambda by 7. We try to get 3-bit, and we try to also drive them simultaneously. But rather than using 3 diodes, we use only 2 diodes. So how? So basically, when you have like a digital metasurface, when you can discretize your phase range, you need, based on your bit, you need diode. But what we did, we used one diode, one reactor diode for this polarization and one for this vertical polarization, right? But although it's is a reactor diode, but we consider different stage of the voltage, assign it to different phase. So rather than using 6 diodes, we use only 2 diodes. And then to save the energy, and because at the same time you want to drive all of these elements individually, what we did, we used this matrix, and only by 1 DAC, which is 2 watt, compared to something around 100 watt, we use just 2 watt to drive this. So there is a row and column, and then based on this and row column, there are some transistor behind it, some voltage cape. In one row, you launch the voltage, and in another one, you control the phase. And because we need to have this kind of track, so this is FR4, because these guys should go through this matrix. So in this case, you have a small size, you have very low specular reflection, you have access to all of your individual elements. And we just drive it with 1 DAC, which has 96 channel, so 47 by 47, the number of elements. But although if you have, let's say you have two only DAC, 96 by 96 would be 9,000 elements. So still, this approach is capable for supporting high number of unit cells. So another approach to reduce the specular reflection. This is actually a pattern, so I can't really show the structure. But we did the simulation with our approach on the conventional metasurface. Same distance, same aperture size. But all of the metasurface, because you're following Foucault-Theorium, and Foucault-Theorium is basically the one that you have on infinite unit cell, right? But in practice, you don't have infinite unit cell. And you see several grating lobe, you see some mirror-like, you try to send the signal 30 degree, you see minus 30 degree as well. You see the specular reflection, and the efficiency is very low. So what we develop, we try to develop one approach based on metasurface inside metasurface. We call it dense metamaterial. And then as you see here, you get rid of all these unwanted beam. And in this case, you just only focus on one beam. And by focusing the beam like this, you will have a huge efficiency compared to the first reflection. I mean reflection efficiency, not total efficiency, because the total efficiency of RIS is very low due to the spillover. The plane wave is coming from nowhere, and you have a lot of spillover. So again, you have low reflection efficiency, but here we try to enhance it. So in this case, we are able to bring down 20 dB specular reflection, 15 dB the mirror-like, and also is capable of 2 dB steering. Reflection efficiency is about 96%, and it could be designed in any particular frequency. So we developed this for sub-6 GHz and terahertz. I mean terahertz, sub-terahertz is 100 gig. So another challenge, RIS is big. That's why some people, they call it large intelligent surface. Why this is big? Because you need large aperture to manipulate your AM wavefront. The main reason, because of the low efficiency. Your base station is far away. If you have metasurface antenna, because the main, I need to emphasize on this. I've seen several work which are reflect array. They call it RIS. The main difference between RIS and reflect array is when you have a reflect array, you put your horn or your feeder in focal point of your surface, and you try to convert a spherical wavefront to plane wave. But when you are talking about RIS, actually there is a base station far away which sending the planar wave coming to the RIS and reflect back again as a planar wave. You can also do something else for near field focusing. Plane wave is coming, then you do the focusing. Means that you're converting your plane wave to a spherical wave. So I've seen there is still some work, they sell their reflect array as RIS. So this is the main difference. And also RIS is not phased array, because in phased array, you have access to your RF. You have input port, you have RF port, then you add some attenuator, some phase shifter. But RIS is something that just reflects everything. And you don't have really access. You can't play with data, for example, right? So that's why it's large, because the efficiency is low. But there are some other way, as Professor also mentioned morning, they call it relay or hybrid RIS. But we try to use, like traditionally people use LNA or power amplifier to boost the signal. But here we employ the transistor. So in this work, what we try to do, if you have transistor, actually you can work at the same time control your phase and amplitude, right? Not only increase the amplitude, you can decrease the amplitude. So you have this access in your algorithm to taper your amplitude response as well, right? And also we try to solve this large surface, make it small, but with high gain, which we use transistor, and simultaneous control on phase and amplitude. So this is the measurement result. This is the normalized gain. So you can see here the static RIS without any transistor for just one way. We normalize it to 0. So we get 11 dB gain more than when you have the static. And this is the prototype under test, right? And the beauty of this, we reduce the size by around 70%. If you calculate the size of the, if you don't have any metasurface, this metasurface can give you 25 dB compared to, let's call it air metasurface, right? So you have 25 dB improvement compared to the scenario which there is no RIS. And the beauty of this, you can also boost the signal from both ends. It's a transmissive RIS. So you may ask, what is the benefit of this transmissive RIS? Some of the transmissive RIS are transparent, you can put it here, but this is active, you can play with the phase. Where you can use it, one example, when you go to the stadium to watch the match, right? Definitely people moving around, they don't need internet, but people sitting around the field, they need high throughput. You always have a problem when you go to, you can't upload a photo or video when you are, or stream the video when you are sitting in a stadium. So just imagine you have some transmissive RIS, right? By manipulating the electromagnetic wave, you can shape your beam, right? So you can get like one beam here, or you can get one beam here, or you can have a contour beam using the active RIS, because at the same time, although you need a large surface, plus active one, because you can play around with your amplitude and phase at the same time, so you are free to do whatever you want. But again, you should have access to all of your units. So one of the way you can solve this size is using the transistor. So next problem is localization. How RIS can find the user. If you have a user is moving around and you have a dynamic RIS, is going to find the location of the user. One thing, very simple way, you buy a radar, bulky radar, put it somewhere, and then it try to find the location that give the information to RIS. Then RIS will reconfigure itself to change the phase to provide enough, let's say, coverage for that particular point. It's complex, not really complex. It's bulky. Is a bit, you see some delay in between because they need to communicate with each other. And there are some algorithms as well, if you see the wireless community papers, but those are not really fast. And if you want to go to iterative approach, sometimes you need to repeat this GA or optimization to find the location. So our solution is ISAC. ISAC within RIS. So this lady is trying to make a video call, and this is the RIS. So she sent some pilot. And if there is no RIS, for example, there is no enough signal to bring to the base station. So the RIS will help the lady to send the pilot towards the base station, right? And then we need to find out the position of this lady. What we need to do, we can design one unit cell, which is hybrid unit cell. At the same time, the unit cell for the communication, and at the same time, some of them, they have RF ports. So one of the main target, actually, I personally follow is I don't want to use any RF chain in RIS because it would be the main price of the base station is coming from RF chain because of power and also price. So we don't want to put one sophisticated programmer behind the RIS. We want to make it cheap. Otherwise, people, they don't buy it, right? Now in millimeter wave coverage, you can buy $500 one small cell, right? So you need to bring down the price and power, right? So what we develop, we try to, you will see the unit cell in next slide, by the way, but here we try to have, let's say only three, you can call it sensor, for example. But the unit cell, which is hybrid unit cell, they have RF port. So these two will help us to find azimuth angle because you know where you locate them. If they are lambda, for example, or 2 lambda or 3 lambda, whatever, you know how the distance between these two hybrid unit cell. So if this is normal, because it's a plane wave, right? If the wave coming normal, so these two, they will see the same face. So you know where is that. But if it's coming from, let's say 30 degree, these two unit cells will see the difference, which is simple d cosine theta. So you can find out where is the angle. And using these two, the same phenomena, you can find out the elevation angle. So simply you can find the location of the lady and you see she can make the cut. And another beauty of this work, you don't put all the processing on base station. Everything will be happening here. So let's look at the unit cell. Oh, we don't have the unit cell. I think I changed it. Actually, the gentleman, they changed my slides. Anyway, so another solution is for millimeter wave. So we developed this, again, hybrid unit cell for 30 gigahertz as a communication, 60 gigahertz for sensing. But in a previous work, we do both communication and sensing at same frequency. But here, because 60 gigahertz is available, there are a lot of cheap available, and the price also is cheap for sensing, localization, radar sensor is around $7, for example, if you want to attach to one of your elements. So we have a large surface, but 64 by 8 by 8, 64 of them, they have RF port. And these guys connect to the radar chip, which are in price also is not expensive. And they do the sensing. So you have a shared aperture between your sensing part and communication part. So this would be ready perhaps in a month. And we will showcase it as well. And these are the results. And this is, we calculate the resolution, how much accurate our approach. And we also studied the behavior of the unit cell for both polarization TE and TM mode, and also you can see the multiple beam coming out from this surface. But those are the unwanted, but we can apply our algorithm to get rid of those multiple beam. So this is that unit cell I was talking about for localization for sub 6 gigahertz. At the same time, it's polarization insensitive, is wide angle, very nice range of phase, useful for ISAC at the same frequency. Another problem is shadowing. So if I'm going to put my big RIS here, so because behind the RIS you have a large PEC, perfect electric conductor, or let's say ground plane, right? So it will reflect back all the signal and there is no coverage inside this building. So one of the solutions is that transparent metasurface, which you can coat on your glass. And there are two ways of doing that kind of thing. So the purpose is you want to bring the signal from outdoor to indoor environment, right? So when wave is traveling from base station to here, of course, it's not coming, you can't ask wave, please come normal. Because when it's come normal, the loss is a small wave coming from different angles. You can't predict. And when wave is coming from different angle, it will experience more loss. Like, for example, if it's coming from 60 degree, roughly around 12 dB loss it can experience. So what you need again here, you need one surface which let the signal come in, but through different angles. Best paper in literature, they achieve up to 60 degree. But in this one, we can see the transparent. You can see the RIS behind it. But actually, there is a metasurface on top of this glass. This is a glass coated by metasurface. It can support -80 to 80. Right? So this is one way of doing that. So fully static, you don't need to be aware of any electricity. You can give the sticker to the whoever would like to enhance the coverage, they go and stick it. But the limitation is if you have coverage outside your building, you will have the same coverage inside the building. As I say, metamaterial, going to invisible the things is like when you put this metasurface, when you coat this glass with this metasurface, is like you remove your glass. So whatever is outside will come inside. So you may ask, okay, in some occasion, I don't have a good coverage outside my building. So how I can use that? So this is actually based on FSS metasurface space frequency selective surface, but you can make a lens using the holographic metasurface to come out with multiple focal point at different points. So we develop an algorithm based on holography theorem. Based on your location, based on the size of the room, you can design or you can generate any contour beam shape. So if this is a line, so you try to bring all the focal point in the middle of the room, or you can have some focal point here after 1 meter, 2 meter, 3 meter, but at the end of the room. This case is like a lens. So Docomo also developed the same thing, but what they did at millimeter wave, you need to go and change your glass. You need to buy the glass from them. But they focus on all the wave to one point, like a lens. And if you have one focal point at millimeter wave, what would happen? You need to go and buy a relay. And like this building, if you have several glass, just imagine how many relay you need to buy, and relay require power. So this case compared to Docomo is much cheaper and more reliable, and you don't need to find the best position to locate your relay as well. So what is next? Let's say if you fabricate the best RIS, if you fabricate the best transmissive RIS, you can do anything. The problem of RIS is whatever comes will be reflected. Noise will be reflected, interference will be reflected. So you need to add some computation behind it. So how? Again, are you going to buy several FPGA or some RF chain to put it backside? No, you don't want to make the RIS expensive. So there is a topic actually initiated by Professor Engata, analog computing. You use metamaterial to avoid using DAC. And this analog computing is useful for future as well, for quantum computing as well. Right? So in Surrey also, we have a colleague who working on quantum computing. You may know him, Professor Gabriel. So he do a lot of quantum, but this is the quantum computing through the analog computing. So this analog computing is useful for parallel processing, is wideband, and it's cheap. So what we did, what you can do with this, like what again today morning we've seen, we need to find we need to estimate the channel. How? Again, are you going to add several processors, sending signal, getting signal? No. Here you put what we do. We put one analog computer behind our surface. We already designed that. So this analog computing metamaterial device, what they do, if you send a signal, they can do first order derivation, second order derivation, they can do integration. And by doing this, you can find out, for example, delay tab. You can find out the length of your tab. You can even find the amplitude. So the next step for our research is to develop reconfigurable intelligent computing surface, but based on analog computing, again, based on metamaterials. And then you may ask, okay, this is a surface. Behind that, you have a ground plane for reflective surface. So there is no way, because that's analog computing metamaterial, they need some surface wave launcher, which is plane, right? So you can have some star shape, or you can have some metal surface which 70% will reflect, 30% go through, and you use that 30% energy for computing. So this was my last slide, and hopefully by next year or next 2 years, we can fabricate this and we showcase it. Thank you so much once again. Thanks, Marco, to invite me here.
First of all, thank you very much for your very nice and interesting presentation, which was really practical and realistic. I actually have a few questions, several questions. First of all, you mentioned that you achieved to have this 3-digit phase shifting RIS practically. And in one of the final, presentation slides, you mentioned that you have a code that you can generate any type of RIS pattern, power pattern, receive pattern. And for example, you can focus maybe on 2 points or multiple points. That is really nice. But is it also possible that to achieve this type of pattern by 3-digit RIS that you already have?
Yeah, actually that one, the last one is only 2-bit, which is 4 states. But what you do, you develop your algorithm based on holography. So you know what phase pattern you require, right? So MATLAB will generate a code, will generate the surface going to CSC or HFSS will be simulated. You see the result. Then it gives the feedback to MATLAB code. The MATLAB code again try to, because he knows only 4 states, right? He knows 0, 90, 180, 270, right? So he tried to go forth and back to find out the best performance based on what you have. For example, if you have analog unit cell, so you don't need this kind of difficulty. But analog one, you need to have a larger size, right? Yeah. So at the same time, you need to think about, of course, there is always a trade-off, and you get something in the price of something, you lose something, but try to make it simple, small, and the last one was only 50 lambda by 50 lambda.
Okay, so you are aiming to achieve as close as possible for that target. Nice. And also in one of the primary slides, you mentioned that you achieved 20 dB decrease in the specular reflection. What was the main reason do you think that you achieved for that? Was it because of this, for example, using 3-digit?
No, that one is not 3-digit. 3-digit was another design. That one actually we develop a mathematical. So let me to make it simple. The most important thing we consider here to reduce the specular reflection was the mutual coupling between elements. Yeah. So we try to count on mutual coupling, and we try to, because you need, let's say, 20-degree phase, but the mutual coupling will change it. So you calculate the first mutual coupling, and you compensate it for another cell. Then again, you do the same thing until the end. So you have one algorithm, you try to use that. And then another thing, because again, when you want to really manipulate your electromagnetic wave, so you should have access to, as much as possible, a small portion of your aperture. So theoretically, if you have a lambda by 10 size of unit cell, you achieve to the best performance. But lambda by 10 is not going to give you the phase range or blah, 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 right? So again, you need to sacrifice something. So here we try to make it small, and then we put metamaterial inside the metamaterial. So each unit cell consists of 4 small unit cells inside, because those small unit cells can catch the mutual coupling around it. Because if you have only 1 unit cell, it will be difficult to compensate the impact of the mutual coupling.
Yeah, good. And also one thing is that I didn't see that much of the operating frequency bandwidth, and also about the one is that, and also about the gain of this active RIS, that you have the overall gain and also the element gain. I would
yeah, so that element gain maybe it's for the millimeter wave one, that is a hybrid unit set. So the range of frequency was different. One of them was 3.5, one of them was millimeter wave terahertz. So we try to show that RIS can work for different particular frequency. You know what I see, what I can believe in future, if you want to use RIS in even millimeter wave or lower frequency, you really don't need the dynamic one, because I consider RIS as an engineered multipass. So you have a device, we generate multipass, right? So you can design a static metasurface with multiple pass. Like now, how signal gets coming here? A lot of scatterer around let the signal come to your handset at 3.5 at lower frequency. So is like these, like a scatterer going and try to follow you? No. Base station will find you based on this multipass response. So if you have some like a coverage problem, you can design a static only, because as I said, I consider it as an engineered scatterer. But when you go to higher frequency like terahertz, because there are not, the channel is mainly flat. You don't have frequency selective channels. So there are not much multipassing environment. Over there, you need to have a precise line of sight between your RIS user and base station. Maybe over there, there are some fixed link. You can use a static, but mainly you need to come out with a dynamic type of RIS. But currently, I believe that for future, for just coverage, you know what I mean? For coverage, a static would be sufficient. But if you want to do the sensing, if you want to do the localization, blah, 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 so you need to play around with your face.
Perfect. Thank you so much.
Thank
you. Other questions? The audience? You? Okay.
Thank you, Professor, for a very nice talk. I was just question for clarification. How do you define reflection efficiency in presence of side lobes?
Yeah. So because you have one source of energy, right?
Yeah.
This energy is going to be reflected. The energy is not going to be disappear, right? So you have some, let's say, loss due to the dielectric loss, for example, which you can calculate. But when you have multiple side lobe beams, it means that your energy is going to be wasted in other direction. And through the simulation, you can see this reflection efficiency by studying the RCS. Because when you have a plane wave in your simulator, you can't really see the gain of the metasurface, but you can check your RCS, and this RCS give you a flavor of how much gain you have, and then you can convert that gain to efficiency.
Then you mentioned there is a just reflecting surface, and then there is the RES. And basically, when we are talking about a practical system, what will be one will be using is a set of elements. It is a network of elements that will be used in a practical system. So, I mean, you think it is enough to talk about a set of elements of reflecting surfaces, or one has to be always thinking about really RIS? I mean, I can add one element. I mean, I understand that a simple reflecting surface would just do a phase shift of 180 degrees. It will send the signal back. Whereas an RIS would give a phase shift which you program.
Oh yeah, I got you now. So sometimes we are aware that corner is a blind spot all the time. Now it works. Okay, so if you are aware of your blind spot, what you do, rather than like building an expensive dynamic RIS, if my base station is down there, so I can fix something here to provide a good coverage down there. Sometimes you want to shape your signal. Because if you have on fully dynamic, if you have access to the signal to the signal in the environment, if you have a protocol, you can do what you want. You can bring it in the stadium, you shape the beam, of the country, you can have it in the surface, you can have it as a both STAR and the surface, and transmit depends on this, like, because network has some cases like in evening time, in midnight, all these factories will be for example, closed. But still at home, they need to or even the parent testing or they use ISAC. So if you are on this kind of system, rather than sending signal to you for other buildings, they can save them and send them back towards the system. So based on the application and the scenario, you can develop your own.
Thank you.
There is this concept STAR RIS, this simultaneously transmitting, and then you talk about this transparent. Are they very much different or similar?
When you design the transparency, you try to bring the thing on. Right? And one thing you don't play around with the main difference between FSS and metasurface is in metasurface you design a new service, you can have access to data. But in FSS you're looking for amplitude.
Okay. Okay.
It's like lifting the signal.
Okay.
This is a transparency. Yeah, you can have a transparency then. But then you have STAR RIS, let's say 50% of the energy is reflect back.
Right.
50% of the energy is going to.
Okay. Right.
Like let's say I can put something here, then they come from this station. At the same time, it can make it coverage for indoor environment.
Right.
And also at the same time can provide coverage for
outdoor. Yeah. Okay, I got it. Thanks.
Okay, we have one other question.
I think we have the guy taking down.
Yeah.
You want to?
Okay, so thank you for your presentation. I have a question about this transparent RIS. So they serve as boosters. So compared to the boosters that they already exist, like a relay, in terms of efficiency in cost, what are the differences? I mean, if we compare them. So sorry, I couldn't hear the first part of the question.
So can you hear me now?
Yeah.
Hello. So basically, relay been there all 20 years back, I think more than. But can you tell me how many operators using relay? None of them. Because why? Expensive. You have power amplifier. And the one thing we should emphasize for RIS is RIS, you don't emit new electromagnetic wave. You recycle them. If now you have one prop and you have one spectrum analyzer moving around this building, you see a lot of electromagnetic wave here, no one uses. If you want to add relay or you want to bring the new base station, a small base station, what happens? You are adding more and more and more electromagnetic wave. But when you use the RIS, somehow you can consider the green communication to some extent. But compared to the relay, yeah, relay is active device. When you have active device, when you have power amplifier, blah, 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 so you can boost the signal more, right? But in terms of price, power, and energy, it's better you go for transparency.
Okay, thank you.
The very last question, then we get to close. I'm sorry, but I guess that you can discuss.
Okay, right. I actually written down a question, but I forgot to ask. So And the thing is that on page 14, if you go there. Yes, yeah, you mentioned the general concept of positioning of rays using this basic angle of arrival difference. But the thing is that theoretically, yes, it is possible to say, for example, using this angle of arrival, we can position the receiver or UE. But practically, did you use any feedback link to really position your receiver? How do you position? How do you get the information of this angle of arrival on the RIS elements? Yeah. Okay. Mm-hmm. Mm-hmm. So you have some sensing elements on those specified. Okay. Perfect.
Okay. So thank you very much. So thank you very much, Mohsen.